My name is Antonio Cavallo, and I've been using Python since 1.5 point something. So it's a bit of time I've spent on using Python. Today I'll be presenting UV and micromamba. There are two package manager. They they share some similarities and some differences. In particular. Um, Let's see. Uh, Oof, I think I lost the control. Um, right. Oof. Okay. Um, those two systems, UV and micromamba, have different histories behind. UV is essentially based on a Rust code, and it's pretty new on the scene of Python package managers. It is package manager, and at the same time is also project manager on the spirit like Poetry, PDM, and other tools likewise. The package they install are wheels, so it's basically based on pip for installation. Micromamba is a completely different history. It came probably 10 years ago, or a bit less than that. But basically, it was an implementation of conda in C++, leveraging a SAT solver called libsolve. The idea of micromamba is to be written C++ for performance, but leveraging the conda packages underneath instead the wheels and using pip for installation. So they have a completely different, but there are things that are similar in basically in the way they handle virtual environments. Those are commons between them, though they cannot be shared. But technically, they create a virtual environment and they use those virtual environment to install packages separately, and they are basically able to create an entire stack, installing also Python binaries for users. In the past, packaging in itself has a long story. It's essentially a role problem because packaging, the mean to deliver an application to user, is basically a role issue. So super user can use to install packages, can use RPM, DPKG, package MSI with a privilege escalation, and so forth. User, on the other hand, they usually install packages using Python wheels. So they can use npm packages, can use MSI on Windows or DMG on Mac OS. But essentially, there are different ways to deploy code on a typical machine. In between the user and super user are developers. They have all the means to transfer packages on the system using, if you are in Rust, you can use crates or Turbo for source code. You can use tools like Poetry, PDM, and PM to create projects. But let's start from an old school way to distribute application. You have two users on the bottom of the screen, and you have a system administrator that needs to deploy two applications, application one and application two. This you can see on the bottom. Well, the system administrator deploy the Python interpreter using super user privileges, install lib A, B, and C, D and E, and then finally the application one and two that depend on the libraries. In the case of application one, library D and E, and in turn B and C, and the application two that depends on it. In this idea, users are completely happy. They have their own application and they can start to use and do something. But time comes and maybe the user decide, oh, I don't need any more application number two. I want to upgrade to 2.1. So the first thing that the administrator will do It's just ripping out libc and the application tree from the system, making the upgrade, and bringing back to the system. Now you see the problem. App one might not depend anymore might not be compatible with the new version of lib. So creating basically unsolvable problem. So the administrator cannot upgrade application 2 to 2.1 without breaking application 1. And this is a problem. So time goes on and people realize that this is not tenable in the long term because still user might want to have a flexibility about their stacks and require different applications. So what end up people doing is, well, taking out basically the system administrator. So there must be a better way to create stacks that basically start from Python, the binary, and creating virtual environment. There are copies or clones from the Python base system. And inside the virtual environment, a user can install all the library they needs, and finally its application in the version he needs. So another user can have his own different stack with different Python version, creating his own virtual environment with this application 2.1 and the dependency. Those two things are completely separate, means that user has a max flexibility. And this is that's the way we're planning to use UV and micromamba to create the entire stack here, from the Python binary up to the final application we want to deploy on the system. This is basically, it's a very flexible way to do it. Clearly, there are downsides to this. Now, the bill of materials, so the entire tree that goes into an application one, it's a little bit more fiddling because it doesn't depend on a super user having super privileges to create this system. So it's harder to keep track of all the packages. But on the other hand, it's very flexible. And it has a completely separate lifetime from the OS. Means that the super user decide to upgrade the system, Linux, Mac OS, or Windows, it won't break apart application 1 application 2.1 because those stacks are ideally completely separate from the OS. So extremely flexible, resilient for system upgrades, but on the other hand, it's a little bit up to the user defining what is inside the system. So there's a potential security issue here, auditing. All right, let's see how do we can create these stacks. I'll keep a picture here just in case. One way to create them is using micromamba and UV. What you see here is basically a Frankenstein Docker image. I'm calling Frankenstein because it's basically a mix between Alpine and a custom-made system. It's very minimal, contains only couple applications. Definitely does not contain Python. Oh, sorry. And on this system, I definitely not root. So if I try to touch hello file etc, it shows you that I'm not root. I'm a normal user, and there's nothing inside the home directory for this user. Now, let's start and show what is installed in here in the systems. All we need is UV and micromamba. There are two standalone binaries with pretty much no dependency. From the size of this, you can see UV, despite what people claim, it's no smaller than micromamba. Yeah, this shows that they're working. Remember, there is the help and so on. So let's begin to build this stack that you can see on the right hand side. So let's start to build a Python 12 stack using UV. What we basically, oopsie, what basically we're going to do here is creating a direct a virtual environment called UV-env0 that contains only the Python executable here, and this env here. Now it takes about 2 seconds. In 2 seconds, UV went outside, download the Python binary, and it created this base and virtual environment. In fact, if I type there, it shows that we just installed Python 3.12.11. 2 seconds is not particularly slow. It's pretty fast. So let's do the same for micromamba. You can see the syntax is pretty much similar. The only difference is the location. Instead UV-env0 director, I will call it a mamba env0. And the difference here is that we stay using 3.12 Python. We want to install 3.13. So again, goes out, download the Python libraries and blah, 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 some other extra library, which it takes 7 seconds in total. It's not too bad. Though it does way more than UV, but as a Python interpreter goes, being Python, it gives you Python 3.13. But that's basically the interpreter, the very basic thing. We want to maybe install some package. And we can do, for instance, we're going to install 3 packages in this case. Rich data is text crawler library, NumPy, that's a numerical library, and PyArrow, that is a file format for large data sets. And using pip. So whenever I do this, I can do UV-env0 Python. Oh, sorry, bin Python. Reach.emoji. And what you can see here is basically using UV, I installed the rich library and I can show the library working. I can do the same with the micromamba. We'll install this library, blah, 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 linking. And I can do that the same mamba, bin, Python, hashem, rich.emoji. Yeah, emoji. And voila. So far, so good. Basically, what we have in this case, we install the Python, we create environment, and we install rich library, and we see that it can work. We did for using micromamba and UV. So for this pretty basic usage, micromamba and UV, they're pretty much identical. There's not much difference here. The real difference it's as we start to use libraries, Python libraries, that they're not pure Python libraries. They're one that depends on extension models, basically C++ or C libraries. Especially one particular complex one is micromamba, bin, Python, NumPy. NumPy is a numerical Python library, which depends in turn on different .so file or extension libraries. Oh, right. Python import or import NumPy and NumPy dot version. And basically, NumPy can be installed using Mamba. And it works. So far, so good. The difference comes when we start to use UV-env. So if we type, let's say, import NumPy, you see this is a kind of error. And this error doesn't come from Python. That comes from the library, in particular one called, what is it, the name? Multi-array umat. Because underneath NumPy, wait, NumPy depends, depend on .so files. And these so files are particularly sensitive to the way they are compiled. Yep. Yep. Get a bit. This is a library that comes with NumPy distribute through UV. UV, as I said, depends on pip, while micromamba depends on conda packages. Mamba dash name multi-arrays mat, and yeah, they're different. The difference, don't know if it's very clear. One depends on a muscle library, which is it's a replacement for libc, and the other one comes from libc. So they are libraries that are incompatible with the system they are installed. The reason underneath that is because there's a philosophical difference between conda packages and pip packages. What didn't we show before is the full picture of these virtual environments. Let's get back to the original idea. We install a Python and we install the library, these white dots. This library are always pure Python libraries, but in case the NumPy, that depends on these red or blue dots. They are extension libraries. Extension libraries, they are this so file that depend on the system. Itself, Python depends on some dynamic library. They are installed on the system. For instance, LDD, number, bin, Python. So even Python depends on these .so files, which are here, system-wide package. Now, pip does something interesting. For each package that has a .so dependency, it includes those inside the wheel file, basically the install pip package, which basically result in this kind of mess, if you like. So like lib.a can contain two different libraries, and maybe lib.e contains the same duplicate library, maybe in a slightly different compatible version, creating exactly the things I showed you a moment ago with the NumPy. Now, conda does this differently, because instead hiding this hidden dependency, this red and blue dot inside the package, it basically explodes them and make it completely visible. This library becomes a dependency to the packages. So lib.a, it will depend eventually from this package, different packages, and not show. So this red or blue dot can be shared between libraries. So avoiding a duplication or slightly incompatible libraries. And this is basically the philosophical difference between wheel and conda packages. Wheel tend to be self-contained, but might have clashing library within them. Conda package instead explicitly depend on other packages that contains solve libraries, making them explicitly. So whenever a solver try to solve these three, it is aware that there are libraries that must be shared between packages. And that's basically the difference between pip and conda. In fact, if you do this mini conda, micromamba, mamba dash p list dash p PWD, Mamba. You can see here the entire list of libraries. In particular, these are the library that are in this three, these blue and red dots. And these blue are just pure Python packages, while instead the list pip list dash pov, you see how differences in terms of dependency. So conda and micromamba basically shift the problem and make it explicit and visible in the solving tree. Pip or UV, they basically try to hide that. In most cases, this works just fine. But if you need control and basically rely on optimized version of libraries, UV, micromamba, conda, they're probably a better solution. But at the basic level, when it comes to pure Python packages, definitely they work pretty much in the same way in terms of what is installed. And that concludes basically the presentation. I want to show you how to create this environment. The difference there, from the user point of view, they're really minimal. They're very similar command line usage. The difference comes when you start to include the external .so library dependencies, in which case the problem becomes more complex. Some can be solved in pip, but other cannot. So it depends on deployment platform you're using. All right. Now for the question. If
Any
there's any.
questions for Antonio?
Hi, Antonio. I think it's really interesting. I'm just curious, how did you get into this, into packaging and all these details? What drew you to it?
I manage on behalf of a couple of groups the entire stack. Back in the days, I was used to build the entire stack from Python and then the Python binary and all the packages that the groups or teams needed. Later, more than 10 years ago now, I started to realize that there would be too much work and briefly moved it to Conda. Back we didn't have the new SAT solver, and it was mostly to support teams or groups I was working with. And it's an interesting problem because it impacts the deliverable. Yeah, mostly out of necessity.
Yeah, okay. No, thank you.
You're welcome.
Thanks for the presentation. I'm curious if you could say more about kind of like a practical scenario maybe where you would want to control like to that fine of a level the dependencies like you get with Conda, like you're showing. Um, like what kind of problem would you be solving where you need um, the way Conda does it versus the way UV does it?
Yeah, that's a pretty clear case for which Conda probably is better suited, especially when I mentioned NumPy because it's a prototype of this kind of problem. NumPy is not a standalone Python library. It's built on top of many extensions. They are built using a Fortran and sometimes extra accelerated libraries like the Intel MKL, Intel Matrix kernel library. Those are optimized and they don't come with wheels. So if you, let's say you have an application, Python application that leverages, I don't know, a matrix operation that built into on top of, I don't know, Intel libraries or accelerated libraries, then conda can solve that problem for you. Otherwise, you need to deploy your own stack, which is not pleasant. And it's pre-compiled, so you don't need to recompile them every time. If you're familiar with the Linux system, conda packages are closer to the RPM model. So that's maybe stretching the stretch a little bit, the similarity, but it gives conda packaging actually it's stretched more in terms of the full control about the building of a package and the deployment, while UV just picks up will rebuild stuff and just deploy on the system. In that way, it's a bit narrower scope.
Can I add an example too, Antonio? Is that okay?
Yeah, of course.
So remember, these are compiled programs. So they're compiled for your CPU architecture, as well as like a lot of times your GPU. And Conda is able to handle those variants based on having those underlying libraries for a GPU or for your CPU instruction. But the wheels, they have to compile a different wheel for every variant. And so you can't really select like, oh, I want this GPU and this CPU combination unless someone's compiled a specific wheel for it. So that's like another example of like where if you're linking all the libraries in the wheel file itself, you don't really have that ability to select like what GPU you want to use on this run or something like that, right? Because the library you installed is specifically just, the one that you downloaded.
Yeah, there's also this case I just remember top of my mind. PsychoPG, which is basically a driver for Postgre. In its default settings, it needs basically to compile it. There's no binary. I mean, there is a binary version of PsychoPG, but in general, if you try to install PsychoPG using a pip, it will need the source code for Postgres. Or if you do the same for micromamba, install -p. I think he has a binary version of PsychoPG too. PsychoPG, which basically doesn't need to rebuild so you can start to use PsychoPG2 on micromamba. Don't need to rebuild the entire package. He has a binary extension built for it. I mean, there are way to get the binary built of PsychoPG, but it's more natural in a conda environment than UV with pip.